테스팅 하나 둘 마이크를 테스트 중입니다. 테스팅 하나 둘 마이크를 테스트 중입니다. 테스팅 하나 둘. 테스팅 하나 둘 마이크를 테스트 중입니다. 핀 마이크입니다. 핀 하하.
어, 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 어. 어. 얘 나오고 있군.
3 invited talks and 7 paper presentations, out of which 2 are remote. So if you haven't done that already, be sure to enter the Discord server. Inside that, we have a SOAP channel with events for every talk. And inside each event, you can post questions even after the talk, even tomorrow or in the next week. But make sure to post all the questions for the video presentations on that, because the Q&A session will be offline. I don't think there's much else to say.
Introduce yourself.
Oh, yeah. Right. I'm Luca Negrini.
I'm Kyung from KAIST.
And yeah, have a nice rest of the day. So we can start with the first invited talk from Xavier, please.
Is it working? I hear myself, so it should be working. Next is screen. Was working. Oh, well, it's working still. So wait, but wrong place. This should work. Okay. So hello, everyone. So first of all, I would like to thank Luca and Guillaume for the invitation. So today I'm going to talk about a static analyzer called MEMCAD, which was designed with a bunch of people, too many of them to cite in a single slide, so I will cite them when I come across specific topics. So what are we going to try to do here? Well, first we are doing static analysis, which in general is a way to compute semantic properties for programs using some kind of conservative approximation. So we are going to use abstract interpretation. And it has a very wide range of applications, some of which are not so commonly investigated. So I'm just going to go through a few of them. So for instance, many people and many tools work on basic safety, so things like proving absence of errors in programs. So for instance, I worked on one tool called ASRE, but there are many more that also try to go for this, like Pharmacy, also Sparrow, which is developed at SNU, not far from here, and many more. So one thing a little bit further is memory safety, so which is to try to prove, again, absence of memory of errors, but for programs that are manipulating complex data structures. So among the tools that work on this, I will just cite one, which is Facebook Infer, or now Meta, should I say. And if we go a little bit further in the safety space, we still look at safety properties. So one interesting place to be is functional correctness, which is to prove not only that the program will not crash, but also that the outputs meet the spec of the function, which is much more difficult to prove than the other properties above, and which is what we are going to look at today. So, and of course, I mean, for the sake of completeness of the discussion, I will just cite a few more that people could also look at, like resource properties. We are not going to do that today, but we could adapt some of our analysis for this. Also, liveness properties like termination, so we are still far from that, but actually also combining the analysis we are going to talk with liveness brings something really nice, which is total correctness, namely trying to prove that a program does exactly what you expect it to do and never always terminates, never crashes. I mean, basically the strongest thing you can expect in the realm of trace properties. And we could also go into the security area, which we could also adapt some of the analysis we are going to talk about today to do. So essentially what we are going to focus on, like I said, is trying to go to the functional correctness from basically tools and abstractions that are more oriented towards the first thing. So this is quite difficult. So we are going to see a number of abstractions for that. So how did we basically do that? Essentially we developed a static analyzer I'm going to talk a lot about today, which is called MEMCAD, for memory composite abstract domains. And the idea of this project was to construct and combine abstract domains for data structures from the bottom up. That is, we just design small abstract domains for specific structures, actually maybe not so small, but at least smaller than if we try to have a monolithic approach which supports everything, and to combine them to have something more expressive. And I am going to talk about some of these combination aspects, which is very important. So essentially today we are going to talk about a tool which is very much centered on memory abstraction. So we are going to first talk only about the memory part, which is not so recent, but which is absolutely required to go a little bit further and to also have abstractions that can talk about content of data structures. Okay? We are going to talk about how we can combine value abstraction together with this memory abstraction, and also to discuss a little bit how we turn all this into some abstract interpreters that is basically the design of which is directed by the semantics. Okay, so here is a very brief timeline. So I'm not going to talk about all these lines, but just give a few specific points. So essentially, this all started in 2007 when I started to work with Boryue and Cheng on tools that was called XISA, which is essentially a prototype of some inductive-based shape analysis, which is basically the foundation of what we are going to talk about today. And after adding a few abstractions, it turned out that we pushed this approach quite far, and the full rewrite of the analysis was required. So this happened in 2011, and starting from that on, we added many abstractions, some of which we are going to talk about today. Like, for instance, I'm going to talk about how we added set abstractions and sequence abstraction to this analysis. And now we have a tool that starts to be quite competent, and we can apply it to try to verify things like functional correctness of a microkernel. So software is not very big, but the property we try to prove is extremely strong. Okay. So what are we essentially trying to do? So here is a very simple example, a little bit contrived. Let's imagine you have some C programs that basically construct some list L and at some point calls a sort function. So this is very classical thing for young freshmen to implement. Now the question is, what if we try to prove things about it? So the first thing we could try to prove is just that it runs safely. And I would say that for quite some time, we have had static analysis that can do that pretty well. That is, you can just give, I did not detail all the code of the function, but that can basically prove that the memory accesses are correct, that we don't corrupt the memory anywhere. This is not so hard. Now the question is, what about trying to prove that this program produces the expected output, which is sorted data structure? Okay, so this is much more ambitious goal, and typically people who try to do that use different approaches like interactive proving or some program verifiers that will actually require the user to provide some invariant. And we are not going to require this, so this is much more difficult goal. Okay, so essentially, in order to achieve this, like I said, we are going to have a requirement for some pretty expressive memory properties logics, but also to talk about content properties like sortedness, which is not something that you can typically find in memory abstractions. Okay? And also, one more that is implicit but very important is that we don't want to have a sort function that always returns a sorted list, but that is basically empty. We want it to return a list that contains the same elements as the input. So we have also to talk about relations across states. This is also quite technical, but very important. Okay, so in this talk, we are going to start with this memory abstraction description, which is not also new, but which is required to basically later extend it with content abstraction, which is going to be the second part of the talk. And in the last part, I'm going to talk about specific verification project, like libraries, microkernel, like for functional correctness. Okay, so let's start with memory abstraction. So essentially, when we look into programs that manipulate data structures, there are many abstract domains that we can use, and very often it is most convenient to be able to talk about separation. If we don't have a way to talk about separation, we are going to be in big trouble when we try to analyze, for instance, updates into memory cells. So, which is a reason why people have introduced a little bit over 20 years ago something called as separation logic. So I will very quickly summarize it. We are going to use the principles of separation logic a lot in the next 20 minutes. So if I don't introduce it, it would not be very complete. I don't want to go through the whole separation logic. So I will just explain the main idea. So the main idea will basically fit into two lines, which is here. Essentially, we have some main connectors that are really capturing the spirit of the separation logic. So essentially, the most important one is the second one, but before we need to look at the first one. So what the first one says is just, we have a memory cell at some address A that contains value B. It seems very trivial. There is not much here. And of course, we are not going to go very far. The second part, which really brings, which is very helpful, brings a lot of power to separation logic, is to have this operator, which is called separating conjunction, which writes down as star. And it combines essentially two heap predicates. So actually what is very important to understand is that each of these formula, H0, H1, or the whole H0 star H1 formula are all denoting set of memory states together with a footprint in a memory. So we are not just saying this memory state has some property, we are just saying this area of the memory state has this property. And when we combine H0 and H1 with star, essentially we just say that H0 and H1 are separate. Both of them, we have a heap that we can split into two parts. One part will satisfy H0, the other one satisfies H1, and we are talking about the whole lot. Okay, so this is very interesting when we try to do updates. So because in this way we can say one program will modify something that is in this region, and this one stays the same. So, and this will be absolutely critical for all the static analysis we are going to implement in the next 20 minutes or so. Now, is it enough? Well, usually not. So separation logic has many more connectors. I'm talking about a few of them here. And actually, I'm just not even citing them all here. There are some very important connectors I just skip. So if we just look at all these formulas and try to make a static analyzer, we have to basically make an abstract domain, the elements of which are those formulas. And essentially, if we try to do that, it's just not going to work. It's going to be very difficult to represent, very difficult to manipulate. Many operations are not going to be easy at all to compute, even in approximate form, very costly, not going to be very good. So essentially, what we are going to do today is to look at how we can construct some abstract domains that takes a fragment of separation logic. So we have to decide which formulas we keep. Out of all those we can express, and to design efficient representation for this fragment. So essentially, this is what abstract domain construction is about. You have a logic. Typically, you would like to represent everything, but you just have to think a little bit more, look at what you really need in program analysis, and do this fragment much more efficiently. Okay, so one aspect of the abstract domain we want to design is that we want also to have an abstraction that is not ad hoc, that is not specific to just one data structure. There are a lot of static analyzers for memory out there, many of which are just dealing with, for instance, lists. We have also a lot of static analysis dealing just with arrays. And we would like to have something that does more than just one of these structures. So essentially, we are going to try to make the abstraction parametric. And this parametricity will later let us have one analysis. We give a little bit of information to it before we start it about what data structure we want to care for one program. And it will just run for that, and not require for us to write another abstraction for another structure, like, for instance, trees, because we only support lists. So how are we going to do that? Well, essentially, we are going to have some basic definitions that we require for users to provide, and that are just some extended version or enriched version of the type definitions. So I'm going to give an example. Let's assume that we take a very classical case. We take a program that will manipulate list of any length. We just use a conventional C list data type. I give 3 examples in the left with a typical representation that the null pointer means empty list. And we have 3 memory states with lists of length 0, 1, and 2. Now, how could we try to describe them all? Well, essentially, we can use separation logics to describe this, provided we add one thing that was not on the previous slide, which is induction. So we just write some inductive predicate, which is here. And what it says is that we have a predicate that corresponds to some memory area and says that A is the address of a list structure if and only if we either have the empty heap region, which is essentially the neutral element for star, and A is a null pointer. So this describes for the blue area in the first state, where there is no blue area because it's empty. Or we have one list element with 2 fields D and N, and the second field N is actually pointing to the address of some other list. So we just write this predicate. And in fact, if we look at this predicate for many data structures, we can actually generate them automatically from the type definition. We can just guess what the induction is and let for users to fix possible mistakes. Okay? So essentially what we're going to do next is combine this small fragment of separation logic that we are going to choose with some inductive predicates, and we are going to build an abstract domain out of that. Okay? So how do we do that? Well, essentially, we are going to have abstract values that are going to boil down to finite conjunctions of graphs. So essentially, why do we take graphs? Because graphs are both very good representation. They can have a semantics that correspond to separation logics, as I am going to show right now. And also, they carry a lot of intuition regarding to what memory structures are. Like if we ask to programmers to describe what data structures they have implemented, very often they will draw some graph. And actually, it's quite likely that the graphs we are going to use inside the abstract state are not very far from our abstract graphs. So essentially, we have this notion of abstract states as a finite disjunction of graphs. Now, what about each of these graphs? We have nodes that are essentially symbolic variables that denote values. So this is quite important to understand. Each node in the graph will be will describe value. And actually, edges will carry basic predicates that are combined by separating conjunctions. So essentially, if we look at a graph, we have a bunch of edges. Each edge corresponds to some memory area, and essentially each node corresponds to some value in the memory, either address or content. And the whole set is basically a separating conjunction of things. Now, what basic predicates do we have? We have essentially basic blocks that are just described by points to edges like this. So essentially what this graph says is we have a block at address A0 with fields F and G, sorry for the small typo, with content A1 and A2, where these A0, A1, A2 denote values. And in the memory, this will look something like that. Then we have inductive predicates. So as I said, we are going to always start the analysis with the data of a bunch of inductive predicates, which can be either user-provided or guessed by the tool based on analysis of the inductive predicates. So we have actually 2 sorts of inductive predicates. If you give me the list inductive definition, you tell me you care for lists. Essentially, the tool will either manipulate introduce 2 kinds of predicates. One is complete structure that is basically going to be written like this and corresponds to a full list data structure. And the other one is actually very convenient when you have programs that traverse data structures, which is basically a segment of a data structure. So this is a segment predicate, which says that basically we have a list that starts at A0, but that's not quite complete. It ends with a pointer to some address, which is A1 here. And if you complete this with a list, then you get a complete list. So this is very important to have when you do structure traversal, for instance. Okay, so when we design abstract domains, we need to care very much for concretization. So what the concretization will do here is it will take a graph into a set of states. I'm not going to expand it completely. Typically, this takes quite a bit of time. I'm just going to stress one very specific point of this concretization, is that when you concretize a graph, let's say you concretize this one, of course, we are going to map each edge to a memory region, which is just we read the separation logic semantics and we unfold it, essentially, so that's not very difficult. but we are also going to give a meaning to each node. And actually, this meaning will be essentially how do you place addresses in the memory. And this will be implemented with a valuation function, which is a function that manipulates, that maps each of these AIs to some integers. So actually, this function is going to play a very important role when we are going to combine this memory abstraction with content abstraction a little bit later. Okay, so in the bottom, I give an example. So here is an abstract state with one graph, with two nodes, with one list. So how can we concretize it? We have several ways. One is to consider the list is empty. You get that with this valuation that maps the content A1 to 0. And the other one that basically just unfolds the list to a list of length 2. So that has a little bit more cells. But in both cases, together with the concrete memories that we get, we also get one of these functions new that is going to be used everywhere throughout the analysis. Okay, so how do we do static analysis with that? Essentially, I just gave a very high-level overview of the memory predicates. Now, how do we do automatic reasoning? So first of all, what we do is forward abstract interpretation. That is, we are going to compute some function that takes a memory state, an abstract memory state before you run a program and produces one after, okay? And the meaning of it is summarized by this formula, which is actually expressing something quite simple. If you start from this S, and if you have any memory plus valuation that is in the concretization of it, if you can run the program from this M and you get some M prime, then for some valuation nu prime, M prime nu prime is going to be in the concretization of the analysis result. So that's very basic statement, and that's how the analysis will work. And whenever we implement one abstract operation to handle condition test, assignment, memory allocation, memory mem-free, and so on, we are always going to think we have to maintain that. Okay? So how do we do? Well, first we will start with very simple case, which is assignment. So if you just have the command xf equal to y dereference g, then essentially what we are going to do in the abstract is very similar to what we would do if we were writing a compiler or a concrete interpreter. That is, we just evaluate the L value, except that evaluating the L value in the abstract means you want a memory cell, and a memory cell is going to be an edge. So we are just going to try to locate which edge corresponds to this L value. The R value corresponds to some values that we are going to store into the L value. So of course, we are also going to evaluate it into the abstract. And like I said, in the abstract, values are nodes. So essentially, we just want this R value to be evaluated into one node in the graph. So, and in this case, it's going to be very simple. If you take this abstract precondition, the L value is this edge in blue. I hope the color is clear. And the R value is going to be the node A prime, so A prime 2. So, and when you have done this evaluation, essentially you can just finish the operation by just performing the update. And in the abstract, the update is just replace one edge by another. Okay, so not all cases are simple like this. If we just take also very similar statement like this one, so you just store into X the end field of L, and for some reason you have some abstract precondition which looks like that. That is, L points to a list segment with some element in the end. Essentially, you want to read some field that goes out of node A3, okay? Now, problem is you don't have any points to edge out of node A3. You have a segment edge. So at that time, the analysis needs to look into the inductive predicate that is given as a parameter, to look into the least inductive predicate. And there are actually two cases. The most common case is that of a non-empty segment. So we just replace this predicate with one unfolded segment here, and then the rest of the update is completely standard, exactly the same as I have shown before. Or second case, the segment is actually empty, so all this area basically collapses down to the empty region, and in this case, we just map the new R value is this node A5. Okay? So the analysis essentially works like this. I just quickly summarize most transfer functions this way. Okay, now very important operation when we do abstract interpretation is to actually generalize predicates. So we have several weakening operations that try to take one abstract state and turn it into something that is more general. So actually we have several operations like this. I'm just going to very quickly give the principle for one, which is abstract union. So if you are given two abstract states and you want to have one that over-approximates them both, how are we going to do that? Well, essentially, we are going to do it step by step. And the principle we are going to use is still based on separation logic. That is, we are going to take two abstract inputs. Each of them describes a set of memories. And we are going to infer some partitioning of the two graphs that is actually going to be connected. So I'm using colors here to denote the partitions. So the tool will come up with some blue partition here that describes a least segment between x and y, and in green, a least tail that starts from y. So actually, this inference of matching partitions is going to be interleaved with the other part of the join, which is to over-approximate each pair of matching partition with the same predicate. So it is much more complex than what I'm showing here, but the principle, you can really see those two steps. The second step is essentially we take the blue area, replace it with a common over-approximation, and do the same for the green. So we get this. Okay, and this defines join operation and also widening, so it has a termination property. Okay, so if we just quickly summarize this part with one example, so here is a C function that inserts an element into a list at a position that gets computed somehow. I give here precondition, which is one graph. What the analysis will do is do the abstract interpretation of each command one by one. And eventually, it will compute a loop invariant, which I give here, which says that we have a list L that points to a whole list here, which is actually split into two parts with a segment, which is actually pointed to by C, and a tail. And when we exit out of the loop, we are going to have an insertion that occurs right at this point. So we create a new element P. There is this memory allocation here. The value D is actually stored here. And we get a new data structure that actually describes the list with this new element inserted. Okay, so this is basically the first part of the presentation. We get this memory abstraction. And as you can see, what it shows in this program is that we start with a program with a state where L points to a list. We get to a state where L points to a list, but we have actually at this point no information whatsoever about the preservation of the content of the value inside the list. We have no information whatsoever about the position of D if we want it. So we need some more work in order to talk also about the content of the data structure, which is going to be the second part of the presentation. Okay, before I get to this second part, I just wanted to mention that we have actually far more memory abstraction that I have shown here. I'm just showing here a small part of the abstract domain. We also have support for a lot of data structures. We have support for array abstraction. We have actually several of them that either partition arrays into contiguous segments, like the one in the top, or that partition arrays into non-contiguous segments, as seen in the bottom. We have also support for hierarchical memory abstraction. That is, we can say we have a data structure, some of which contains a data structure and unfold this way. So we have actually a lot of choice in the abstract domain, a lot more than what I can show here. By the way, how much time? What is, I forgot to ask. Sorry?
Still half an hour.
Half an hour, OK. And also, if anyone wants to ask a question anytime, please feel free to interrupt me. OK, so that is essentially what I wanted to say about the basic yeah, please.
Thank you. For the abstractions, are all of them available at all time, or do you select the abstractions you need based on the program at hand?
OK. So in fact, when you start the analysis, by default, you have a set of abstractions that will always be active. You can pass options to the analysis to enable or disable abstract domains. And essentially, it does not change during the analysis. What can change is how effective each abstraction is. That is, we may have, the analysis itself can, to some extent, self-parameterize itself and say, at this point, we don't need this abstract domain and still have it here, but not represent any information in it. So I hope my answer is, but actually it's a very good question, and maybe we can also come back to it in the second part where there will be much more abstract domain choice.
Cool. Yeah. Thank you very much.
Sure. Okay, so actually before I move to the second part, I wanted to make a few comments on implementation. That is, we often talk about how we design on paper static analysis. I find there is a lot of work to do to actually implement them well. So I will expose some of the choices that we use in this work, and maybe they are not, of course, the only choice you can make, but I can at least explain why we work this way. So for the abstract domain that I have shown so far, we use only immutable data structure. We use functional code, and so this is written in OCaml. And this is absolutely, this is for us, we found absolute requirement, which is, well, first of all, maybe ironically, it is very safe regarding to updates. That is, we have a lot of safety in the abstract domain in its implementation that just comes from the fact that we have data structures that are all immutable. We also get a lot of seamless sharing of common regions across different abstract states. So actually, we get a lot of power from this choice to have only immutable data structures. This reduces cost. This reduces also memory cost and also runtime. We can sometimes do very tricky things. For instance, when we have condition and we detect that two parts of the abstraction are physically the same, then we can immediately say the join is exactly the same. So we skip a lot of work. So essentially what we use as data structure is a lot of sum types in the OCaml setup with indexed maps and sets. So probably the data structures I use the most to implement those graph structures are here. Okay. And the analysis itself is almost purely functional code. We have references only for options and logging, basically. Okay, so now we are going to move to the second part, which is how do we do with collections. So far, we only talked about the memory layout. So if we try to also talk about the content, apparently things are going to be a little bit more difficult to describe. So we are going to discuss this a little bit now. So essentially what we wanted to do is to verify not only preservation of the data structures, but also something about the contents. We have to add to the abstract domain things that tell us this data structure contains a set of values or a sequence of values. Maybe if we want sets, we actually want sets with multiplicity, so multi-sets. So we want to augment the abstraction, which is so far just about memory, with the ability to talk about all these kinds of structures. So this is actually not trivial at all to move from one pure memory abstraction to something that can also talk about content. So essentially, we have to cope with a few abstraction problems. So one major problem is how to first find collection abstractions. There are fewer collection abstractions than you can find, for instance, for numerics or for memory. So maybe we need to design some. Actually, I will show a few of them. We also have to find how to engineer the combination. Like having two separate analyses is clearly not an option. We want a product abstraction where actually we can talk about the content together with the memory shape. And we want also the two abstractions to communicate, to exchange information seamlessly. So this is not a simple goal. So we are going to first start with a very basic first step, which is how to talk about value properties. So we are not going to do content right away. We are going to get to content in 2 or 3 minutes. We are first going to just imagine we would like to talk about lists, but we want to also add one more piece of information, which is that all the elements should be positive. That is, we are going to have operation in our program. It should not only maintain the fact that we have a well-formed singly linked list, it should also maintain the fact that values are all positive. So if we try to basically define this property and to write an instance like to parameterize our abstract domain, if we just write an inductive predicate, we can easily do it like this. So essentially what this predicate says is basically essentially the same as a singly linked list predicate. I just call it LPOS because we are talking about lists of positive numbers here. And I'm just highlighting in purple some predicates that I attach to each of the two cases that were already in the singly linked list inductive predicate, and that have a meaning in terms of values. Okay? So actually there is one predicate that was actually two that were already here, but I did not emphasize this too much in the first part of the talk to basically separate concerns a little bit. But in the first case, we needed to say that we have a pointer that is null, because anti-list corresponds to null pointer, so we already had a little bit of numerical information in there. Second is, in the second case, we have also a predicate that says that A should not be null because we don't have anti-list. And we also have this additional predicate, which is really asserting that the list is containing a positive number, which is the field A1 is a positive value. Okay? So we can write some inductive predicates that capture the meaning. So the question is how to extend the analysis so that it will do not only just basic singly linked list predicate without numeric information, but be able to care with such information. So essentially, we are going to get there in two steps. The first thing I would like to stress is that if we just try to write this predicate, and let's assume we can write predicate LPOS in our abstraction, and we just hit the unfolding button. So we have this operation, which is unfolding, which I mentioned in the abstract precondition, so it is implemented in the analysis. What would it provide? What would it compute? And what insight can we take from the output of this unfolding to actually design the abstract domain? So let's look at what I would like my abstract value to look like. Well, if I unfold this LPOS predicate, I will get an unfolded shape graph, like you can see here, well, which is not surprising at all. It is exactly what we saw in the first part of the talk when we talked about singly linked list. And I also would like to materialize those predicates and to say that some of the nodes that are symbolic variables representing values have some numerical information attached to them. So for instance, in this case, I want to say that A0 is non-null and A2 is a positive value. So that gives a lot of intuition about what we want to do. If we want to have this combined abstraction, what we want to do is to combine together with a shape graph that I talked about in the first half of my presentation, together with some numerical abstraction, the dimensions of which are going to be not the variables in the program, but the symbolic variables, which are the node in the graph. So this is really the single most important bit that lets us move to the first part, to the second part of the presentation, which is so we are going to augment our shape abstraction with some numerical abstraction, but instead of saying things like variable x in my program contains a positive value, we are never going to say that. We are always going to say some symbolic variable, which occurs to be maybe the value of x or something else, has the property of being non-null or positive. Okay? So if we formalize this a little bit, we get a new abstraction, which is a combined abstraction. So we have already seen the first element of the pair, which is just one shape graph. And the second element is going to be any abstract element of your favorite numerical abstract domain. It could be intervals, it could be polyhedra, it could be octagons, it could be linear equalities, anything you like. You just take one abstract state of that domain, but you have to be careful for one thing, that the dimensions in n sharp should always be exactly the nodes in S. Sorry. If you just look at all the nodes in S, which I write as AS, these are the dimensions you are allowed to use in the numerical abstraction. Okay? And the analysis should maintain this at all times. So actually, this construction, you can view it as a kind of product of abstract domains. Actually, it's not quite a reduced product. It's something slightly different. Actually, there is a formalization of it done by Arnaud Venet some 25 or 30 years ago, which is called co-fibered abstract domain, which is a little bit technical, but this is essentially what it's doing. Okay? So now, if we talk about the analysis itself, what is going to happen is we are just going to have a choice that you actually do before you start the analysis. So this was a question a little bit earlier. How do we set up the abstract domain? Well, when we launch the analysis, we choose one abstract domain could be, for instance, any variant of the apron numerical abstract domain library, could be something else. Actually, in our case, it is a combination of many of those things. We have a big reduced product inside the numerical domain. And the crux of everything is that the shape analysis, the shape abstract domain will maintain consistency of the symbolic variables that are in S and the dimension in N. That is, whenever we do an operation, maybe the dimensions in S will vary because we add edges, we add nodes and remove nodes. And we are going to modify N accordingly. Okay, so this is actually pretty tricky, but extremely powerful. Okay, so now I would like to get back to collection. I promised I would talk about content, not just values, so let's get there. So essentially what we have is, now we would like to express things like, we have a list that stores a list of elements that we can express somewhere. So what idea are we going to use? We are just going to use very similar inductive predicates, but we are going to add some symbolic variables that denote sequences, and that are going to also be used in the abstraction. So I'm first going to write a predicate. For now, I'm not going to care for the abstract domain. I will get back to the abstract domain in 2 minutes. So, and this inductive predicate will just tell us that we have a list that stores some sequence of elements that is captured in some symbolic variable E, the semantics of which is not a concrete value in terms of an integer, but a sequence of values, a sequence of integers. Okay, so here is the predicate. So we have, again, 2 cases. So A is the address of a list, the elements of which are sequence E, if and only if either we have the empty region, A is null, and the sequence is empty, or we have a non-null pointer, A is not null. We have a shape formula that basically describes what we are used to, with one small difference, is that now the inductive call to list also carries some sequence symbolic variable, which I will call E prime. And we also have to have one more relation to capture the fact that the whole list contains sequence of element E. That writes down as E is equal to value A1 dot sequence E prime. We just concatenate them. So this is just an inductive predicate where E has semantics of a sequence, and we could actually have something that is maybe a slightly less expressive, slightly less strong, where we would just say E is a set, for instance, or E is a multiset. We would just write almost the same thing. We would not use the same connector here, but that's pretty much it. Okay? So essentially, this is how we add collection information into the inductive predicate. So now the question is, how do we concretize abstract states? How do we define and concretize abstract states? So the first thing is, so far we have used valuation functions that map symbolic variables that were variables A, A1, A0, A1, and so on into integers. We are going to extend this with one more case, which is symbolic variables of the form E, E0, and so on, and the meaning of which has to be a sequence of integer. Okay? So we are going to also use a combined domain, which is exactly the same as what I did for values. This is exactly the same definition. The only thing that changes is that now symbolic variables can be either just values or sequence sets or multisets. Once we have done that, well, all we need is collection abstract domains. So what we did is we did quite a few of them, actually. We have first a bunch of collection abstract domains that focus on sets, so they forget the order. So they abstract sequences, but only the first thing they do is the abstraction throws away the order of the elements and describes some set property. So we have inclusion and membership constraints. We have linear equalities, so with some algorithmic that is actually a little bit inspired from the car abstract domain, except that we operate on sets. And we have another abstraction that was designed by a PhD student I co-supervised with Evan Cheng, Arlen Cox, which is essentially representing predicates of that form. Intersection of a bunch of set variables is equal to the union of a bunch of set variables with a graph representation. A very, very tricky representation. So we can invent many more collection domains, include them into the analysis very easily. Okay. We also have introduced abstraction for sequencers. So again, predicates are not surprising. We have emptiness, non-emptiness. We have linear equalities. We have size constraints, bound constraints, sortedness constraints. So actually, those mean that you also have connections together with the numerical abstraction. So actually, it's a very tricky reduced product of abstract domain to implement. Same for the min and max constraint. And the sorted predicate, we handle all the logics to talk about sortedness. OK, so I think now I probably don't have so much time, so I will skip this. 15, OK, well, no, I will not skip this. So this is just an example of one abstract state where we use our logics now to talk about not only the memory shape, but also the content, the collections that are stored inside the data structure. So we have here two variables, L and X, that contain some value. And actually, the content of L is the address of a list, the content of which is a sorted sequence of elements that are all greater than the value of X. So that's the kind of property we can express. I will not discuss in detail the concretization. The only thing I will stress is that now when I concretize this, I get not only a memory, some set of memory region, I did just draw one for the sake of space, but also memory region together with evaluation function, which map all the nodes and also sequence variables into values. And in this case, E is mapped to the sequence 8, 15, and 33. OK, so now if we talk about operations in the analysis, essentially we need to come up with sequence, set, multi-set abstract domains. I talked about the predicates. What about the operations? We have all the classical lattice operation, join, union, intersection, widening, top, bottom. The main operations are essentially add a constraint, so which is essentially what we call guard in most numerical abstractions. We just have to have a guard into the sequence abstraction. And we have also a SAT operation to check, to discharge collection constraint, which we have to use whenever we try to prove, for instance, that some predicate describes a sorted list. So we have to ask for the sequence domain, is this symbolic list E actually sorted? Okay. So, and when we implement this combined analysis, we have also to talk a little bit about how we combine those abstract domains in the code. So like I said, I like to make a few comments about the implementation itself. So for the data structures, I said earlier that we use immutable functional data structures. Now, how do we structure this? We use a lot of modules and functors in this OCaml language. So if you just look at any functional language with module systems, this is what we use. So with essentially this convention that a module is very often one abstract domain, so module signatures for us are very important because they just list all the operations. And very often next to the operations, we have commands that describe the concretization, the soundness condition, right? So it's, now if we were to try to prove static analyzers, which some people have done in other projects, this would be a coq module with also the definitions of the soundness condition of each operation. So now that's for the base domains. Now most abstract domains are parameterized by others, so we use a lot of functors, which are just ways to make modules parametric with other modules. And we use this a lot to say we just take some abstract domain and enrich it with some other functionality. We take numerical abstraction, we enrich it with sequence abstraction, for instance. So that's one functor. And actually, we found that this is actually a very useful programming setup to basically break down the design of the analysis in many small pieces, each of which can be designed separately. So it's actually quite, I mean, without this, we could not basically survive. So as of now, so in fact, while preparing the talk, I just said, how many functors do I have? How many abstract domains that are parameterized by another abstract domain? And I counted 50, so maybe I was wrong. I did that on the flight, so anyway. So some of these are actually just proper abstract domains that just add a bunch of predicates, some of which are actually not really adding new predicates to the abstraction. They are just factorizing some part of the operation implementation, some of which are doing logging, some of which are doing also some tracing that we use to improve the analysis. But essentially, this is the design that we follow. Okay. So now I'm going to get back to the last part of the presentation, which is how to try to verify not just basic safety, but actually functional properties using that. So this is going to be a bit shorter, but we are going to start with an example. So let's assume we have some predicate, which is essentially the last one I introduced. So here we are talking about list together with the constraint of the sequence of the elements that are stored in it. So we can say A is the address of a list that contains the sequence of elements E. Then what can we do with that? We can actually specify logic triples that express that a function is correct. So for instance, here I just assume that I have two lists, L0 and A1, and I call some append function that destructively appends the list, the second one into the first one. We can write the precondition as a formula using our symbolic, inductive predicates. We can also write a postcondition, which is what we expect the function to compute. And once we have written this, we can just start the analysis. So what it will do is just translate, oops, I think nothing has changed in my side. I did not see the screen blink or anything. Okay. Should I unplug and replug? But I believe, no, it's still working, so. Good, not so good. Okay, so back to this verification goal. Once we have written that, oops. Okay. So I hope it will work for more than 10 seconds. The analysis will basically translate the precondition into some abstract state, do forward analysis of the body of the program, and then just call some inclusion check function to try to prove that the abstract postcondition that was computed here is actually satisfied at this point. Implies this formula. So that's how we verify code. So the first thing we did after we implement this collection abstraction is just try to verify, so that was part of the thesis of Jocelyn Giet, who graduated last year, a bunch of functions for lists and trees, actually. So we took some libraries for lists, including some sorting algorithms, some merge sort, for instance, insertion sort, and we try to prove that they are safe. Well, that was not what we wanted, but also that they are functionally correct, which is what we wanted. So in fact, we just did the analysis first without sequence abstraction. We expected it to always succeed. We had a surprise that actually in some case, it does not succeed. That was a surprise to us because it shows that actually in this case, if we don't try to have a little bit more embedded into the abstract domains than just memory reasoning, it will fail. So that was quite surprising. But in most cases, we could prove safety without the sequence abstraction. If we add the sequence abstraction, the analysis costs quite a bit more. Actually, we reduced a little bit the slowdown since I made this table, but still cost is quite a bit more. And we have actually functional correctness proved into a large number of cases. So of course, this is just a bunch of the things we did, but I just wanted to show a few things, like some sorted algorithms. We could just basically prove that without any information inside the function, the analysis will make it to prove the postcondition. Same also for some operations on a binary search tree. So this is actually quite strong properties that were proved without intervention. We just specify the property, we let the analysis run, and it works. Okay, so now that was not really our end goal. Our end goal was to verify some actual system software. So we just took some microkernel, which is called FreeRTOS, and we took one instance, so it's not a very big kernel. It's a kernel that is really meant to be used in embedded microsystems. So it's a few thousand lines of C code. You can parameterize it a lot. So we took one instance, and we just looked at the data structure we have in there, which are a lot more complex than what I have shown so far. So we have essentially some doubly linked list to describe the list of tasks that are ready, the list of tasks that are delayed, also with some order on some tick events to say when a task is going to be reactivated, when it is delayed. So it's actually quite a lot of things to describe. We wrote specification for that. So we have a file that basically says what is the invariant we expect for the operating system. That is, at one point, what do the data structures look like? And for each system call, we just also wrote one line, which is typically so we just expect before we run the system call to have this global invariant plus one condition, which is activation condition for the system call. And what is the post condition we expect for the system call is also typically the invariant of the OS plus one condition, like maybe we just turn one task from delayed to active. Okay? So we just wrote all these specifications, and we run the analysis for each system call, and this is what we got. So we have analysis times that range between less than a second to something like 2 minutes for each of the system call of the instance we consider. So this is just a part. I mean, there are many more system calls and many more things, but total runtime is something like 300 seconds on desktop. And memory usage is just at most a few gigabytes. And for each case, we actually could verify the functional correctness properties that we specified. So actually, this is very strong properties that we got here. Okay, so what we would want to have in addition to that, which we don't do because we only do safety analysis, is termination. So actually, I think that would be a nice next project to add termination into this, because we would then get total correctness. But I would say that in this case, termination is really not going to be very hard because the loops have pretty trivial, well-foundedness arguments do not seem very difficult. So the big difficulty in each of these cases, especially some of these system calls in the bottom, is to preserve the data structures that we have here and to reason over structures where we have typically 20 or 30 variables, each of which points to pretty complex data structures of this kind. Okay, so now to conclude, what are the key points that we wanted to get to today? So first, I would say that static analysis can be made very precise. So of course, it costs more, and we are not going to scale this to the Linux kernel tomorrow, that's for sure. But most people think static analysis is going to try to be quite cheap and not to compute very strong properties. Actually, here we prove, I think, that in certain cases, you can try to make static analysis able to prove very strong properties of programs. Maybe not the biggest programs at this point, but we can work on scalability from that point. Second point is abstract domain design. Takes a lot of effort, but is actually very rewarding. So in fact, when we started the Xiza project, we took a lot of time with Evan to craft the notion of valuation, how we map the nodes to values in the same time as we map these graph edges into separation logic predicates and memory regions. And this is essentially what let us later have this collection abstraction also fit into the framework. So a lot of work, but very rewarding later to work on the basics of the abstract domain design. And the last thing is also, the more we research in that area, the more we find there is a lot of unexplored space in terms of abstract domain design. That is, for the collection abstraction, I see very few people who try to basically design new abstractions, and actually there are a lot of predicates and representation of these predicates that could be tried to make this a little bit more lively, as was done for the numerical abstraction in the last 40 years. Okay, so these are just 3 main points. Now I'm very happy to take questions, and thanks again.
Anyone has questions?
Hello again. So first of all, thank you very much. It was really interesting. And can you say more about how function calls work? Because you have a separation logic domain, how do you do function calls in general? When you have to, because you have a specification for another function, you want to call that, or do you just inline the function?
Okay, good question. So in fact, let me get back to this here. So in fact, we do whole program analysis. That is, we assume here this is a whole program. So actually, this is not exactly how the analysis would work. Actually, we would just give precondition and postcondition for the main function, and then nothing else is annotated. So functions that are called by main, or even in this case, maybe append would call some other function. This is not annotated. Now, one thing we have that's not working for all abstract domains is support for recursion. Because, of course, when we have to handle recursive calls, this is like much more difficult. So actually, we don't have support for all recursive functions at this point and for all abstract domains. One thing I would like to mention is that actually I just have this timeline that shows some work that we could have explored more and tried to port to all abstract domains, which was done in 2011, which was to do some relational stack abstraction. That is, when we have recursive calls, something that's very difficult is that when the call stack contains data structures that have to be abstracted together with a heap. And we essentially, we just said at that time, well, call stack is just data structures. We can just use basically the same data structure abstraction, which is very powerful. We found it works in pretty complex but small cases. Trying to make it work in all cases much better it would be a project that we still would like to work. So this is some idea we had in the past, more than 10 years ago, and did not completely maintain. So, but that's how we do for functions. Yeah.
Thank you.
Anyone else?
Yeah, Guillaume. No, sorry. Sorry, I could. Well, I mean, the whole analysis is handling destructive updates. So if you have, if you modify data structures that break pointers and replace pointers by others in chains, we handle that, yes.
Oh, okay. Thank you.
I mean, this is essentially one of the big points of the memory abstraction that we have. Otherwise, we could get to something less powerful, which is also very interesting, which is based on type systems.
Any more questions? No? Do you have support for user-defined data structures? If someone comes up with a new implementation of something.
Okay, so essentially, in fact, when we, so maybe I could have explained this a little bit better. When we start the analysis, so the analysis will give you a choice. Either it will scan the type defs and try to make one such predicate for each type def that it finds, and then you just get the analysis running like that. This works when you have fairly simple data structures, but if you start to have a lot of pointer relations that are really things that we cannot guess, they are really in your own designer's mind, then essentially you can just write such a predicate, and the analysis will take this as a kind of template to basically support the abstract domain implementation. So the short answer is yes, the whole point is to support user-defined data structures.
And you talked about scalability in the end. How far did you push this analysis? What's the biggest code base that you managed to analyze?
Okay, so I think biggest code must be the FreeRTOS instance, which is about 1,000 lines, for which we actually only do functional correctness. That is, if we just drop the precision, like I think maybe I can, that is, if we just do the same thing as we do here, that is, we deactivate some part of the abstract domain, we just remove the sequence abstract domain and say we just want to see safety, it will not work because the data structure invariant require us to come up with stronger arguments. So we have to go with this stronger argument to actually prove the code. It is about 1,000 lines of code and 5 minutes for this very strong property.
Okay, thanks again, Xavier.
Okay, thank you.
And I think we are a bit early for the first coffee break, so we have a bit of free time.
So it's Siddiq David Baker Effendi from Stellenbosch University. It's Xavier Pino from StackGen. It's Andre Michael Dreyer from Whirly Labs. And last but not least, Fabian Yamaguchi, also from Whirly Labs. And I guess some last few moments of setup. And here we go. Please take it away.
Testing. Oh, great. Thanks. Hello, everyone. Welcome to my talk on scalable language agnostic chain tracking using explicit data dependencies. This work was part of some of my PhD contributions to an open source project called Yearn, and I'm presenting this on behalf of the contributors and Fabian, who is the prime owner and maintainer of the Yearn project. So what is the motivation for having this kind of data flow analysis in the project? And while the motivations are that whole program analysis is expensive and difficult to scale, and if we want to try to ignore the external libraries and reduce the problem size, we have additional challenges, such as how do we model and define the behavior at call sites that have unresolvable callees, and if we do summarize this in some way, how precise should these summaries be, and can we achieve quick feedback without sacrificing recall with all the way to solve those additional challenges. This is a motivating example we use in the paper, and just to explain it briefly, we have object U defined by a static external call get value. Then we have a object V defined by a simple constructor. We then have an external config call that defines some control flow, and we have another definition of result, which is the return value of a dynamic dispatched call, u.transform v. And then we have the result of this and v as parameters to an internal static call bar, which then passes the parameters to sync.addValue. So this perspective of arguments to calls and operations being defined, used, or both within a method can be represented by a data dependence graph, which is the stable representation that we will use. And the edges on this graph go from where variables are defined to nodes that use it without a prior redefinition. And if we add control dependence, we can get the program's dependence graph, which is what we'll use to visualize this code later. But the big question now is, how do we handle callees that we cannot see? So these external libraries that we are ignoring. Well, so we have in the blue rectangles, the declarations, and we can see at the top that U and V go to our u.transform v result. And then we have that result goes to the internal call bar result V. But how do we encode the possible data flow side effects that happens in u.transform v, as these objects could have sort of the data flow from v could affect the receiver u in some kind of way. There could be side effects that set fields or load fields from receiver to the result of the call, etc. So that's really the big question. How is this going to be encoded? And well, we choose to use the system dependence graph representation, which has separate nodes for the in arguments and the out arguments. As an example here, we show that the transitive dependency, which is essentially a dependency between two nodes that undergo a number of steps in between by a single edge. So by the presence of an edge between input argument u and output argument u means that data flow is retained, but data flow from u could flow to v, and perhaps v is the only argument that defines the data flow in the return value. So this presents a call site local transitive dependence representation. So extending this by over approximating our data dependence graph, we can then encode via the output arguments that u and v might actually have some kind of implicit flow to the call of bar that is first dependent on this transform call. So the proposed solution is a whole program dependence representation that can be updated when the behavior of calls to external libraries becomes known. So these transitive dependencies between the input and arguments at the call sites are encoded with the system dependence graph approach, and we allow users to annotate what actually happens at these call sites without recomputing the whole graph representation. So this is also important to support partial program analysis to keep the problem small, but remain sound by default when we encounter unresolvable callees. And sound means that we assume that all input arguments use and define all output arguments and the return value, and we remain intra-procedural until query time, so that we're isolated from the call graph analysis, which could be changed at some point. The approach is built on the code property graphs generated by Yearn, which I briefly mentioned is the open source project this is contributed towards. So first, we add a stable data dependence representation on top of the CPG. And the way we do this, so that we don't have to recompute the graph every time that we maybe redefine the behavior of a callee, is over-approximating all the call sites as if they are unresolvable callees. Of course, this will introduce many invalid parts, but these will be discarded at query time. And this is either done by analyzing the data dependence. If the callee is resolvable, we can then actually perform a data flow analysis on that procedure, or refer to a user-defined semantic annotation if one is supplied, which I'll go into detail later. So obviously, because it's over-approximated, discovering additional flows requires no effort. That is the default. And annotations only are required if we encounter false positives that we would like to eliminate. So annotation language is very simple. It mirrors this input-output pair logic. It consists of the procedure's full name and the input-output pairs, which define the edges between an input argument and output argument. And if no edge is present when a summary is present, then it is assumed the flow is killed or sanitized. The parameters are either by index or name, as some languages use named arguments, and special indexes are used for the return value, so -1, and the receiver 0. Such an example looks as follow. So if we want to describe that Euler transform V sanitizes argument 1, and the receiver propagates flow to the return value, receiver is 0. Since receiver is not sanitized, we must have the sort of default edge, so 0 to 0, and that 0 goes to -1, the return, to describe the data flow between the receiver and -1. No pair is present for the first argument, thus it's assumed to be sanitized. For example 2, let's assume that the receiver taints argument 1 and neither argument defines the return value. Then we can have our 0 to 0 and 1 to 1 to say that neither argument is sanitized, but that the argument the pair from 0 to 1 describes that the receiver taints argument 1 in the output. So a very simple annotation syntax that is quite easy to write, but again, the limitations we'll just go into a bit later. So how does this work when we actually encounter internal procedures? And this is where I describe on a high level the algorithm of the paper. So the query, this is sort of now the on-the-fly query data flow analysis, consists of a set of sources, a set of sinks, and the user-defined or generated semantic annotations. As the semantic annotations is also attached to a programmatic API that one can generate from the CPG itself. And the goal is to determine all source sink pairs for which there is some kind of transitive dependency. And how is this practically done? Well, we break the query up into tasks, and the results from each tasks could either be standalone or generate new tasks to be solved at method boundaries. So such an example could look like the following. So we have our semantics. This is Scala code, by the way. Yearn has a default semantics object that describes basic operators. And then we have our engine context, which is a simple configuration object. And then we define our source query, which has the cpg.call step describing the call, or the return value thereof, the sink, which will describe the argument 1 of add value, and then we call our reachable by query. So we begin by just creating initial tasks. Initial tasks will be based on the sink as we do backward analysis, in this example, and this will be the 3-tuple of a node, initial empty path, and the call depth. Now, before solving any task, let's consider what a result look like, as these results will create new tasks. So we have two main parameters, which is the path and the call depth of a result, and the path is consisting of a list of tuples, where n is the path length, v is the node, and a boolean indicates some sort of completeness. And what this completeness is a boolean indicating whether the associated method of this node has been resolved in the process of generating this task, or resolving it has been deferred to a future task, which means that we'll essentially be creating new tasks from this node. So how are new tasks created from incoming results? Well, this is a k-limited analysis to ensure termination. So we first ask, is k larger than our maximum depth? If yes, do not generate new tasks. What this results in is an incomplete tasks with no dependent task, and this will ensure widening and termination. First is v1 a parameter, so we start at, since we're going backwards, we're sort of looking at the head of the path. So if yes, look up the corresponding argument against the call graph. So whichever call graph is in place, if none, then this will approximate. And then generate the task as follows. So we have our 3-tuple of the argument, the path, and k plus 1. Is v1 an argument to a call without an associated semantic? Then, and r1 is false, so it's a incomplete item. Then if yes, the corresponding output argument will be the node of the task. And just to note that operators also modeled as calls, so this includes your assignments, generic binary operators, etc. And how do we solve these? So a task again is this 3-tuple, and assume we have a global result cache to memwise incoming results. So for each outgoing DDD edge, we have SO, which is the parent of V. Is there an edge between SO and V that is valid? So recall that every DDD edge is over-approximated, so it's not necessarily valid by default. The validity depends on if there's a semantic definition that says this is valid. If it is, then we have a result of S0, and then the second part of the tuple is if it's an argument, an output argument, which will determine if a result is going to, the result is going to be a new task. And otherwise, is there a cached previous task result, in which case the prepending the path would be a little bit longer, and we save a bit of computation. To not have incorrect cache results, we have the following cache key, which is the node, the call stack, and the call stack up until that point, and the k depth. Then we, at the bottom, if the result above contains a source node, ensure that one of the result entries starts at the source node. We then deduplicate and return the results of V, and the final result of the query are all the entries in our result cache that begin with something in the source set, and then there's a final deduplication so that we don't return subflows within larger flows. An example of that from Yearn is on the table on the right. This is without defining any semantics or imports. The graph on the left I won't explain too much in detail, but as you can see, all those edges are these sort of over-approximated input-output relations that where Yearn will assume there is some kind of dependence. And this is one of the flows that's returned to the sink. So for the evaluation, we use taint analysis. So again, we ask, does a source define data at a sink? And what is our indicator of success? Essentially, we use F1 score, which is a little bit more about how many true positives do we get, more biased towards recall. And since that is perhaps too biased to include for something that over-approximates, we also include J-index, which is a bit more balanced for false signal. So we use 3 programming languages to evaluate against, so Java, Python, and JavaScript. And related work that we evaluate is SemGrep as the fast, cheap option, and CodeQL as a bit more of the detailed, expensive option. In the data sets, we use Security Bench Micro, Security Bench Micro JS, which is a contribution of this paper, which is a transpiled version of the Java equivalent, and Florat, which is an extension of an existing benchmark that we complete. Just to briefly explain this table, we have yearn with and without semantics. With semantics is the SEM entry. So for the Java equivalent, we have better recall and precision than the rest, and faster runtime. But yeah, SemGrep has much faster memory, or better memory rather. Then we have CodeQL as the next best in terms of precision, and then lastly SemGrep. The runtime of CodeQL is quite high, and by the way, this is partial program analysis, so the libraries are excluded. Next for Python, on the second row, we have larger recall, but far less precision. The precision you can refer to the J-index, as we have much more false signal. But again, CodeQL is a bit more precise here, and yearn is the fastest, and SemGrep is the least precise, uses less memory. Then with JavaScript, we see that, again, CodeQL has equivalent recall and better precision, but we're still faster and use more memory. But now let's ask about the whole program analysis. So we include libraries because Java uses bytecode and SemGrep doesn't support that. That's excluded here. The runtime looks a lot worse in terms of the Java example. We're a bit more equivalent to CodeQL. I know CodeQL sort of packs the runtime with it, so perhaps it is doing much more of a whole program analysis than we maybe intend in the evaluation. But we still have higher recall. In case of Java, better precision. But one thing that's very interesting, besides the high recall, low precision CodeQL trend, is that for JavaScript, we somehow have more precision. So I guess that suggests that having access to the callees actually improves upon whatever is happening in CodeQL. Cool, so let's get to the limitations. Obviously, defining data flow from input to output parameters is very simple. While it is an intentional design decision that makes improves the speed of analysis, it doesn't model field loading and setting in general, object memory and heap, or side effects on modifying global state. The task solving does not account for dynamic object shape properties, so defining properties on the fly. That's something you can do in a lot of dynamic languages. Object aliasing, we do weak updates, and variables captured by closures is not fully baked. The speed and memory part of the evaluation does not isolate the benefits of the underlying database. CodeQL, for example, uses SQLite. Yearn uses a columnar graph database. And the precision of the data flow analysis, of course, is tied to the call graph. Whether we can resolve a callee or not depends on when something will be over-approximated. And so to conclude, we present a data flow analysis system in Yearn that is capable of language-agnostic analysis, is robust to missing dependencies, allows for annotating semantic behavior of callees in order to reduce false positives, and compared to the evaluated related work, has better runtime performance compared to CodeQL, but is not as precise for dynamic languages, has higher precision than SemGrep, but not as performant, but overall has much higher recall than both due to this over-approximation first strategy. Great. Any questions?
Are there questions? So given we have only 1 minute, maybe I would like to ask a question. So in your design, you first decided to over-approximate all of the flows, right?
Yes.
And then later on, you decided to somehow limit this call depth to, I think, 5 or some value
Yes,
k.
yes.
Could you comment on how these two decisions go together?
So I have some extra slides here. Yes. So with the value of k, the higher value is more precise, and also using k-limiting is just allows for a much simpler design. And obviously a high value of k will then become very expensive. The lower value would mean more widening happens, and we have faster termination. But to decide this value, essentially we took really big benchmarks from various papers. So defects4j is one that's popular, bugs in pi is another. And for varying values of k, we ran a bunch of data flow analysis, looked at a bunch of sources and sinks that are present in each library, and just ran that. And we found that k was a good point before we start to see this massive, sort of almost exponential growth. So that is sort of how we optimized and chose that value. As per CodeQL and SemGrep, that equivalent is not extremely configurable from what I had a look.
Awesome, thank you. So then let's thank Sidik again. And then the next speaker is going to be from the University of Paderborn, and he will urge us to pick our call graphs well when we're doing IDFS-based data flow analysis. All right, please take it away.
Yeah, so welcome everyone. Myself Palaniappan Muthuraman and my colleague Kadire Karakaya. So we are from Paderborn University, Germany. Our professor is Mr. Eric Boden. So I'm here to present on our topic, pick your call graphs well on scaling IFDS based data flow analysis. So to give some context about our research, so we are from static data flow analysis research group. So when we give a target program, a static data flow solver, which consists of IFDS solver in our case, will take help of a call graph and will try to give some good information whether the given target program has any bugs, or does the given target program has any privacy leaks, or is there any security vulnerabilities present in the target program. So given a context of static data flow analysis, now let's dive into the motivation of doing this research. So this is a basic Java taint analysis example. As you can see, there is only one main class, a main method, and there are three other classes, class A, B, and C. So the class hierarchy looks like class A is a superclass, and classes B and C extends the class A. And there is a method foo in all three classes, and in the class A and B, the foo method returns some arbitrary integer, and in class C, the foo method returns a secret value, which in fact is supposed to be a secret and should not be visible to the outside world. So if we execute this program in a normal Java compiler, as you can see in line number 4, there is a foo method that's getting called on object B. So it is evident that if we run this in a Java compiler, the value of 1000 will be printed, and the ground truth will be there are no leaks in this program. But here we are trying to do static analysis. So the important thing I mentioned in the previous slide in static analysis is we need a solver, in our case IFDS solver, and a call graph. So what exactly is call graph? So call graph is a data structure that can find the potential callees that can be called during the execution of the program. So in call graph, we have methods as the nodes, and the connection between the methods are called as edges. So here I will be using two terms called imprecise call graph and precise call graph. The term imprecise call graph might contain some spurious edges. That means the methods that could not be executed at runtime will also be present in this call graph. So considering the same example, we can take CHA, that is class hierarchy analysis, the most imprecise call graph per se. So when using this call graph on this program, we will get the result as the foo methods on all three classes will be called. So if we use this call graph in our data flow solver, our analysis will say there is a leak in the program, but we can say that there is no leak by the normal Java compiler. And when moving on to the precise call graph mostly tends to contain only edges that might be executed at runtime. It does not have any spurious edges. So for this example, I will be taking rapid type analysis called RTA. So if we use this employees RTA call graph, we get foo in both classes A and B only will be called. So using this call graph, our result says there are no leaks in the program. So comparing both the precise and imprecise call graph, the only difference that we can see is there is only one edge less in both the less compared to both the call graphs, but the analysis results kind of differs on opposite sides. So now this raises a question of, does the variation in the number of call edges have any impact in the precision of the client analysis? So the theoretical implication that we can claim here is the precise call graph will maintain precision even with less number of edges, that is only the edges that might be called at runtime, and it might also scale well because it does not have any spurious edges to walk through. So this theoretical implication was given so long before this research was conducted. In 2018, our professor kind of said in his paper, higher precision yields better performance. But there is no conclusive proof for this. So we challenged our professor and we took it, and we said to him like, okay, we'll try to prove this. So as throughout this talk, I was until now I was talking a lot about call graph. So for this implementation, for this evaluation, we needed a call graph framework that can generate call graphs for both Android and Java applications. But given the scope of applications or call graph frameworks that are present in the research area, there is no such framework that can generate call graph for both Android and Java, and it has a pool of call graph frameworks to select from. So one can argue that Suit Java optimization, bytecode optimization framework can generate call graph for both Android and Java, but the downside of it is it has only 4 techniques, 4 call graph techniques. And recently, Kilin state-of-the-art points to analysis framework that can generate call graphs for Java applications, but there are 2 downsides in it. One is it does not support Android specific features, and it works only for applications that have single entry point. So based on these mitigations in the real world, mitigations in the research area, we were forced to develop a framework called QCG, we called it QCG, that can generate call graph for both Android and Java applications, whether it can be Java normal applications or libraries, whatever it is. And Kilin can generate call graphs, 31 different flavors of call graph with case sensitivity, we kept it as a maximum of 2. So the technical description, I'll just explain about how we developed QCG. So for Java libraries, unlike Java application, we don't have a specific main method. So it does not have a single entry point. So what the solution approach we took here is, we considered all the public methods of the library as a potential entry point, and we used iterative work list based processing. By this I mean, we'll take all the public methods and we'll start from any arbitrary public method, and then whenever we find a new method that's not present in the work list, we will just add it to the work list, and then until the work list is empty, we will be propagating it, and then the final call graph will have all the potential edges that might be called during this execution. Now talking about Android applications, the same problem as Java, Java libraries, it does not have a specific entry point, and presence of callbacks that is being handled by Android library itself makes the call graph generation more difficult for Android specific applications. So the solution approach we did here is, so in Android there can be multiple activities, multiple components, inter-component communication and stuff. So everything will be logged in the manifest file. So first we found the manifest file in the Android application, and we found out all the activities that are present in this, and there are core set of 6 callbacks that Android lifecycle has. So if any activity extends this callbacks, we will just take that call graph as a potential entry point, and there can be multiple potential entry point. So we coupled everything into a dummy main method, and we used that as a starting point for our call graph generation framework. So given the motivation and the implementation that we did for this evaluation, now it's time to look at the research questions. So here we were focused on 2 research questions. The first one is precision. We wanted to see how the call graph precision impact the IFDS based precision of the IFDS based client analysis, whether the call graph precision has any good or bad impact on the precisions of the IFDS analysis. And the second one is performance, whether the call graph precision impact the scalability of the IFDS analysis based on runtime or memory consumption. So the experimental setup that we did for research question 1, as this is based on precision, we need a benchmark. So we took a benchmark called Taint Bench that consists of 39 different Android malware apps, and it has a ground truth for it. And we employed Florodroid as the IFDS based client analysis. So Florodroid is a state of the art static taint analysis tracker for Android applications. So for Florodroid, the that are supposed to be given is the Android application and the specific source and sync file. So what exactly is source and sync file? It will tell the FlowDroid that which APIs are considered as source and which APIs are considered as sync. So FlowDroid as a static data flow solver needs call graph. So whenever FlowDroid needs a call graph, it will ask QCG, the framework that we developed. So the QCG will in turn return the call graph to FlowDroid, and the FlowDroid will give the taint analysis results, and we compare it with the ground truth of every application, and we will calculate metrics such as precision and recall. So this plus precision and recall gives the result of our research question 1. So as I mentioned, there are 39 taint bench applications, and as I mentioned earlier, QCG can generate 31 different call graphs. So we had 1209 runs for this. We aggregated all the results at the end. So there are 31 different call graph configurations, and we don't want to select all for this further evaluation. So what we did is we selected the top 4 configurations from Killin and the most commonly used configurations from Suit. This selection is based on the precision and recall and also the number of edges. So here we compared CHA's number of edges as the benchmark, and as you move from the bottom of the table to top, you can see as the precision increases, the call graph edges tends to decrease, and the precision also keeps on climbing. But the recall here seems to be very limited. I will explain about that in the next slide. So based on this experimental evaluation of research question 1, the takeaways are we used K limited context sensitive pointer analysis and object sensitive pointer analysis, and we limited K to 2 because we don't want to make the analysis so time consuming. So we just kept K to 2, and it is evident from our evaluation that the more the value of K, the analysis results are more better. Compared to 2 context sensitive and 2 object sensitive analysis, we got a better result, and it is precise than 1 object sensitive and 1 context sensitive. And as you might have seen, the recall is very less for the all the configurations, and this is not an interesting results from our evaluation, because the taint bench researchers even in their paper quoted that taint bench when used with FlowDroid applications, gave very less recall, and it's also been in line with our experiments. And the most important takeaway that I consider from this experiment evaluation is the more precise call graph will always leads to more precise taint analysis, but it doesn't guarantee a better recall. So when considering call graphs for IFDS based taint analysis, we should not only consider precision, we should also consider about their recall. So now moving on to the research question 2, that's based on performance. As the first research question is based on precision, we took some benchmarks, but this is based on performance, so we need some intensive applications. So we used applications from APKs from Play Store. We downloaded top 20 APKs from the Play Store, and we used the same FlowDroid and QCG for it. But now instead of 31 different call graph configurations, we used only 8, and 4 of them from Killin and the 4 from Suit. And we use the source and sync files that are present in FlowDroid, the generic source and sync files, because we don't have a curated source and sync file for every applications. So now as a result, here we did not care about the ground truth. Here we just cared about the performance metrics. The performance metrics are number of interprocedural edges, the number of propagations that happen with the IFDS solver, the runtime, the memory, and this answered the research question 2, that is the impact on performance or scalability. So for every application, we have 5 hours time budget. We had 220 GB of memory budget, and we ran every application with every call graph for 3 times and aggregated the result. So this diagram shows the average time spent on call graph analysis and the taint analysis. The bottom dark gray version is the time it taken for the call graph analysis, and the top one is the time taken for the taint analysis. As you can see, the first bar, the CHA, as I mentioned in my example, most imprecise analysis, took very less time in call graph construction, that is 10% of the time is spent in call graph construction, and the remaining 90% of the time is spent in analysis time, taint analysis. as we move towards the end of the graph, you can see the time spent in the average time spent keeps on reducing. That is, the more precise call graph spends very less time in the analysis, and the implication here is if we spend more time in generating call graph, it might produce it will produce very precise call graph that might not have spurious edges, and because of no spurious edges, the analysis will be so fast. So that's the implication from this that can be taken away from this diagram. And comparing the runtime and memory consumption. So again, as you can see in CHA, CHA took around 3000 seconds for average analysis time, and it took around 150 GB of memory. So the theoretical implication here was that the most imprecise call graph will consume very much time, and it also consumes very much memory. And as we move from CHA towards the more precise call graphs, we can see that runtime and the memory consumption tends to decrease because of no spurious edges. It has only the edges that will be executed at the runtime. So the takeaways of the research question 2 is when we are using more precise call graph, the runtime and memory consumption tends to decrease, and that's what the theoretical implication was given in the given by our professor, and we kind of found that in real world as well. The time spent in building a precise call graph will pays off in the analysis time, and that's also evident in our diagrams. One such outlier result that we found here is a more precise call graph not always gives a good scalability, because it is taking a longer time to build. It's kind of same as the CHA, the most imprecise one in some of our examples. That's what I called as outliers. So to conclude our research, we first developed a framework called QCG that can generate call graphs for both Android and Java applications, and it bridged the gap between Flowroid and Kylin, because Kylin is not sound for Android. And we did extensive evaluation to find out the precision of impact of the call graph's precision on the IFDS based analysis. So the takeaway from research question 1 is, when evaluating these call graphs, one should not only consider the precision, should also consider the recall of it. And the takeaway of research question 2, when using fine-grained call graph algorithms, that is the call graphs that are generated based on pointer information, seems to be very precise, and it also results in less runtime, less interprocedural edges, and less memory. And again, I mentioned in the last slide the outlier. In some applications, we found that the usage of the precise call graph, that is the pointer analysis based ones, seems to be an overhead, as it took longer time than the normal CHA or RTA. So the most precise one is not always precise for all the use case. So yeah, so that's it from my side. Thank you.
So are there any questions?
Thank you for your presentation, and I am wondering that you said there are tendency between the precision of call graph and the performance of data flow analysis, and you mentioned that in some cases that is not correct. Can you give me any specific example?
So one second, I have an example over. Yeah, so this is one example. So here we can see the CHA took only 290 seconds for this application to be evaluated overall, but the usage of this precise call graphs, as this point analysis based ones, took more time in the call graph construction. So because of the more time spent in call graph constructions, so the time the overall analysis time spiked up. So
I'm asking, is there any code property that caused such a result?
Oh no, we didn't look into the code property as why does this takes more time. We just found out because the applications are so big, Like we took the top 20 applications from Android, and it was not so easy to find out exactly why this happened.
Okay, thank you.
Okay, so then we have, I think, time for one more question, if there is one more. If not, then let's thank the speaker again. And next up we have Ilya Muravev from the St. Petersburg State University, who will tell us about some work that he did together with Semyon Grigorev, also from St. Petersburg State University. And the topic is universal high-performance CFL reachability via matrix multiplication.
Thank you. Hello everyone. My name is Ilya. I'm from a company called Exploit, and today I'll be presenting universal high-performance CFL reachability via matrix multiplication, which is the work I did with Semyon Grigoriev. So first of all, let's talk about what context-free language reachability is and why we care about it in static analysis. Let's start with a very common problem, which is determining if the value of some variable A can flow into another variable B. You can imagine how this problem arises in all the different types of static analysis, but how do we actually solve it? Let's say we have a very simple program. It consists of an identity function called ID and a main function that calls the identity function twice. Here, A flows into B because ID of A is assigned to B, while C doesn't flow into B because ID of C is unused. But if we naively construct a sparse value flow graph, we'll see that A reaches B, which is expected, but also C reaches B. So we need some way to discard the path from C to B while preserving the path from A to B. One such way was proposed by Thomas Reps, and the idea here is to use edge labels. We use opening parentheses for the edges that correspond to function calls, and we use closing parentheses for the edges that correspond to function returns. And we also use subscripts to differentiate between different call sites. And now we only consider those passes whose labels form a well-nested parentheses string. That is to say, they form a word from the DIC language. For example, the path from A to B is well-nested, so A can flow into B, while the path from C to B is not well-nested, so C cannot flow into B. In this particular example, we focused on the DIC language, but in general, in CFL reachability, any context-free language can be used to impose the path constraints. For example, if we want an analysis that is both context-sensitive and field-sensitive, we can use various context-free approximations of the interleaved DIC language. So how do we actually compute CFL reachability? First of all, we receive the path constraints in the form of a context-free grammar. In the case of the DIC language, the grammar may look like this. Next, we identify the rules that have more than two symbols on the right-hand side. Here it is the third rule, and we simplify such rules. Here we do it by introducing a new symbol called n. And now that we have a simplified grammar, we can start adding new edges to the graph. First, we look at epsilon rules. Here we have an epsilon rule for the symbol s, so we add a self-loop labeled s for each vertex of the graph. Next, we can look at vertices x and b, and notice that there is an edge labeled s followed by a closing parenthesis edge, so we can use the force production rule to concatenate those and create a summary edge labeled n1. Here we use the subscript of 1 because the closing parenthesis has a subscript of 1. And now we have an opening parenthesis h from a to x, followed by an h labeled n1 from x to b. And here we can use the third production rule to create yet another summary h. And this time this h is labeled s, so we know that a reaches b via a well-nested path. Notice how we can't apply the same logic to create a summary h from c to b, because in this case the subscript of the opening parenthesis doesn't match the subscript of n. All of this can be quite compactly translated into the language of linear algebra. This is important because linear algebra operations are highly efficient on modern hardware. Okay, so the graph is naturally translated into the adjacency matrix, whose elements are sets of symbols. And as for the grammar, we map its rules to the set multiplication rules. And now that we have the set multiplication operation defined, we define the set addition operation simply as the set union operation, and we can start propagating CFL reachability via matrix multiplication. For example, if we multiply the adjacency matrix by itself, we'll find out that there should be a summary h labeled n1 from x to b. And this brings us to a baseline matrix-based algorithm for CFL reachability called matrix CPQ. This algorithm is very simple. It starts with an adjacency matrix T and then keeps adding T squared to T until a fixed point is reached. This is pretty much the same as the classic Floyd-Warshall algorithm, with the only difference being that matrix elements are sets. Matrix addition is actually an element-wise set union, and multiplication is defined with respect to the grammar. Originally, matrix CFPQ was proposed in the context of graph databases and evaluated on navigational queries. Here, the bar graph shows query execution times. Matrix CFPQ is shown in red. And as we can see in this domain, it outperforms other universal CFL reachability solvers. But navigational queries on RDF graphs are unrelated to program analysis. So naturally, we tried running matrix CFPQ on program analysis tasks. We took a few data sets that contain C, C++, and Java program graphs, and grammars used for value flow, alias, and points to analysis of different levels of sensitivity. And here are the execution times we've got. Here, matrix CFPQ is still shown in red, and as we can see, on program analysis tasks, it is no longer in a clear lead. In fact, in the majority of the cases, matrix CFPQ actually exceeds the timeout of 3 hours. Here I use small crosses to show cases where we have timeouts, and also to show cases where some non-universal solvers are simply incompatible with a particular analysis. So why is matrix CFPQ so much slower on program analysis tasks? There are actually 2 reasons for that. First of all, these tasks typically require many more iterations for convergence. And secondly, we often use quite large grammars for program analysis. That's because when we want field sensitivity, we add a separate production rule for each field. And when we want context sensitivity, we add a separate production rule for each call site. So how do we deal with the first problem of having too many expensive iterations? Here we need to realize that on the later iterations, the matrix T barely changes, so we can speed up things a lot, especially speed up sparse matrix multiplication by only considering those elements of the matrix T that actually change. In other words, we can replace T times T with T times delta T, where delta T is simply the last change of the matrix T. And we also need to remember that matrix multiplication is not commutative, so we need to multiply T by delta T both on the left and on the right. Okay, let's look at how this first straightforward optimization impacts the execution time. Here the baseline is shown in red, incremental matrix CFPQ is shown in orange, and in cyan we have the previous state of the art. As we can see, the incremental version is certainly faster than the baseline, but doesn't quite reach the performance of the previous state of the art. Before we can tackle the next issue, that is poor scalability with respect to the grammar size, we need to talk about how the baseline matrix CFPQ represents the adjacency matrix in memory. The thing is, linear algebra libraries work best when matrix elements have a fixed size. But in our case, matrix elements are sets of different sizes. The original authors of matrix CFPQ recognized this problem and decomposed matrix T into multiple Boolean matrices. For each symbol x, they created a separate Boolean matrix T superscript x that simply shows which cells of the original matrix contains the element x. Using this Boolean-based representation, we can compute, let's say, T times T by simply multiplying appropriate Boolean matrices chosen based on the production rules. For example, let's consider the production rule for the symbol n from the Dyke language grammar we looked at earlier. From this rule, it follows that for each value of I, we can compute T times T superscript ni by simply multiplying Ts by T opening parenthesis I. As you can see, the number of Boolean matrix multiplications the baseline matrix CFPQ needs is equal to the number of call sites. In our implementation, we utilize linear algebra libraries better and do all of these multiplications in batch by simply using block matrix multiplications. So let's look at execution times once again. Here, the version of matrix CFPQ with all discussed optimizations is shown in yellow. We can see that it is significantly faster than the previous version, and that it also starts to get competitive with the previous state of the art. But we still have 3 more optimizations to go. The first of these 3 is optimizing matrix formats. The thing is, some matrix multiplications are faster in row major formats, while others are faster in column major formats. So we actually maintain 2 copies of the matrix T, so we can choose an appropriately formatted copy based on the multiplication we perform. And at this point, we spend so much effort optimizing multiplications that actually additions often becomes a bottleneck. The issue here is that on each iteration, we add an extremely sparse matrix delta T to a much more dense matrix T. And that causes a complete reconstruction of the whole matrix T. And to deal with that, we actually don't perform the addition and simply memorize all the matrices that need to be added together in a set of matrices called T tilde. So now when we need to multiply, let's say, delta T by T, we actually need to multiply delta T by each matrix in the set T tilde. So if we let this set grow uncontrollably, we will soon end up with too many multiplications. So to deal with that, at the end of each iteration, we actually have a partial merge phase, during which we try to identify matrices of similar sparsity and actually sum up those matrices. Okay, so let's look at execution times. Here, yet another version of matrix CFPQ is shown in green. We can see that in some cases, the 2 optimizations I just described actually result in a slight slowdown, but overall we get a significant speed up. And most importantly, we actually reach the state-of-the-art performance in the majority of the cases, and we still have 1 more optimization to go. This last optimization is related to the fact that the same context-tree language can be generated by different context-tree grammars. And actually, for 2 grammars from the CFPQ dataset, we found equivalent grammars that result in a better performance of the respective analyses. This last optimization is purely empirical, so all I can do is show you execution times one last time. Here, our final version of matrix CFPQ is shown in dark green. We can see that it is much faster than the baseline, and that it is also faster than the previous state-of-the-art across different static analyses. Of course, there are some exceptions. For example, in the leftmost case, the fastest solver is actually gigascale, and that's because for this particular analysis, there exists a specialized data structure that gigascale uses. Okay, so far I've only talked about execution time, but we also need to consider correctness and memory efficiency. So first up, correctness. In all considered cases, optimized matrix CFPQ obtained results aligned with other solvers. In terms of memory efficiency, our solver is generally in the lead, On a geometric mean basis, it uses about 30% less memory than the second best, thanks to efficient memory management in the linear algebra library. Although I need to say that in rare cases, other much slower solvers do use less memory. In the future, we plan to generalize our optimizations to other variants of matrix CFPQ. Specifically, we want to target multiple source matrix CFPQ, since it can be used in on-demand analysis. And we also want to look at all passes matrix CFPQ, since it can be used in a mutual refinement algorithm for interleaved dike reachability, which itself enables analyses that are both context sensitive and field sensitive. And besides that, we also plan to further boost the performance by avoiding some redundant derivations and offloading the most intensive computations to GPUs. And that's pretty much it. Thank you.
So are there questions for you? So maybe I can get the ball going. So you said that for different grammars, your approach, the efficiency differs. Could you characterize what makes a grammar better or worse suited for your approach?
Basically, what we did, of course, thank you for your question. And what we did is run our approach and profiled which grammar rules take the longest time to process. And we don't have much intuition of it. Right now, we use kind of greedy approach to eliminate these rules and replace them with different rules, or run it again, identify worst performing rules, and replace that. So I think it needs more studying to understand which rules are worse and which rules are better in terms of performance.
Thanks. Then Xavier has the next question.
It's working. Thanks a lot. Yeah, thanks a lot for the presentation. So if I understand well, your end goal is to offload the computation to the GPU, as you just said. So in previous works where people try to do this with some part of the abstract domain representation, one effect that was observed is that in the transfer of data from normal memory to GPUs, there is some offset, some cost that comes up. And that can actually be more than what you gain by doing some of the computation on the GPU. So do you think this will be a problem in your case, or did you not consider this at this point quite yet?
Thank you for your question. It is indeed true that transferring data to the GPU is can be more costly than actually performing the operations. And here we have some results with the baseline matrix CFPQ. It's not actually really our results, it's other people worked on running baseline matrix CFPQ for RDF graphs on the GPU, and they got the performance boost. But in our case, the performance boost may be less because our optimizations actually make matrices more sparse, which diminishes performance boost. And also, we don't really need to perform all the operations on GPU. There are some recent works that use approaches that combine CPUs and GPUs and actually even perform the single matrix multiplication operation partially on GPU and partially on CPU. And perhaps we can benefit from that.
Okay, thank you.
And that's for sparse matrix multiplication, I need to clarify probably.
Just to give one reference I was thinking about some work by, I think, Jacobazzi and a group of people with him, where they actually turned some numerical abstract domains into GPU, and I believe that was octagons, and they had the effect I mentioned. So that
the work I mentioned is not about static analysis at all. It's a work titled Heterogeneous Approach to SPGEM, I think something like that. And SPGEM stands for Sparse General Matrix Multiplication.
So we have time for one last question, which comes from over here.
Thanks for the talk. So regarding the representation of metrics, so as you presented, so when the age has symbolic values, like the example you showed in the very beginning, the context sensitivity, right? So how do you efficiently process those symbolic values? And some values may just like the transitive, right? Transitivity. And some values has to, you have to be aware of those context sensitive matching. Would this affect the effectiveness when you do this multiplication?
Okay, let me go back to the slide you mentioned. You probably are talking about this slide. And we actually don't run any symbolic execution or any abstract interpretation. So we actually care about data flow analysis without caring which values are
But
flowing.
imagine if you traverse from A to B, right? So you need to match the calling context, the return size as well. Then you basically, in classical way, you have to like basically match them and pop those from the stack. So once you reach from A to B, then B you don't have any symbolic value when you keep traversing. So how would you handle this in the matrix multiplication?
Oh, it's via the grammar. We have, let me find the slide. We have the grammar defined via how we define matrix multiplication. When we multiply an opening parenthesis 1 by n1, we get a set containing s. But when we multiply an opening parenthesis 2, let's say, by n1, we get an empty set.
Okay, probably in the interest of time, we can talk offline.
All right, so let's thank Ilya one last time. And then our next presentation is actually going to be remote. And it's going to be from some people from KU Leuven and Rémi Prévé from INRIA. And it will be on Beyond Affine Loops, a geometric approach. And please recall that they will not be able to answer questions here. So if you want to ask them any questions, please register for this Discord. And in the Discord, you will be able to find a SOAP channel. And in, yes?
They should be listening, so they will be able to answer questions.
Ah, okay. So they will hear it and they'll reply by audio. Okay. Yeah, that makes it easier.
So numerical methods. Okay. Idea is similar. So we have this complicated polynomial system. So in this setting, it's called a target system. And we have a starting system, which is much simpler to find a solution. And if you use this homotopy continuation, you can track the solutions of a target system from a starting system. Okay. For example, there is a package called homotopy continuation in Julia. You can use it to find a solution. The last one is SMT solvers. SMT solvers can determine the satisfiability of logical formulas combining with Boolean logic with mathematical theories, such as integer or real arithmetic. For our case, we have conjunction of polynomial equations, and we would like to check whether it's satisfiable. For example, Z3 can check it. If Z3 can prove if it's satisfiable, then it can give us a rational solution, and we can use it to synthesize a loop. In our case, the last method actually works very well on our benchmark set. Okay, now let me explain some experiment results. We implemented our code in Macaulay 2. Okay, let me explain the table. The parameter S represents the number of non-zero equations defining our parameters P, and this also represent the number of solutions of our polynomial system, which is exactly the same as number of possible loops. Okay, the parameter N represents the number of variables in a loop. Parameter M represents the number of invariants given invariants, and the parameter D represents the maximal degree of polynomial invariance. If you see the table, for most of the cases, our algorithm terminates. Okay. In the second table, we present timings in seconds. So there are two timings. The first time is the running time of our algorithm. The second time is time of Z3. So by using our algorithm, we can construct a polynomial system that gives you correct values for these parameters inside that map. Okay. And now we have this polynomial system that we can use Z3 to find the rational solution and actually synthesize a loop that satisfies given invariants. If you see the table, for most of the cases, if our algorithm terminates, Z3 can actually find the rational solution. And also these benchmark examples, we got it from these three papers. So these three papers are exactly the same as the papers in the state of art slide. Okay, now let me summarize. So first we explain a method how to convert the problem of synthesizing loops that satisfy given invariants into the problem of finding a solution of polynomial system. And after that, we actually gave some methods to find the rational solution, which is useful because we need to find the rational solution for our polynomial system, which is constructed by our algorithm. Also, we have some ongoing works. The first one, the polynomial systems defining invariant sets have some specific structure, and we would like to use that structure to compute invariant sets in a faster way. The next one is we would like to synthesize non-trivial loops. As I said before, we might not able to synthesize a non-trivial loops. The last one, in our work, we only consider equation invariants. So of course, the next step is like consider invariant inequalities. Therefore, our problem is that synthesizing polynomial loops that satisfy given set of invariant inequalities. Okay, thank you for your attention.
Okay, so are there any questions? Okay, so maybe to kick things off, I can ask the first question. So first of all, thank you for your talk. And then I noticed that basically your algorithm, it either works within seconds or you immediately, more or less immediately run into a timeout. Do you have any idea what the characteristics of the problems are where your algorithm works well versus those where you run into this 300-second timeout?
It depends on as monomials. We need to synthesize our loops. Like if the number of monomials is okay, let's say fewer than 6, then it usually terminates in seconds. If a number of monomials is greater than 6 or 7, it usually reach the time limit.
Okay, thank you. Any other questions? That does not seem to be the case. So thank you again for your presentation, and thank you for being here with us this morning. And yes, let's give him another round of applause.
Thank you.
So that was the last talk within this session. We will continue here again at 2 p.m. And I think now there is lunch. And I'm being told lunch is either here or in this great ballroom A. So you can either stay here or make your way there. And then we see you again at 2.